Hey everyone! Today we're going to talk about some really fascinating new research that basically flips one of the biggest ideas in AI right on its head. It suggests that the way to get to smarter AI, well, it might not be about getting bigger, but about thinking a whole lot smarter. In the AI world, there's this one idea we hear constantly. Bigger is better. To make a more powerful AI, you just need a bigger model and more data. It's like this endless arms race for sheer size. But what if that's not the whole story? What if a smaller, more clever model could actually run circles around the giants when it comes to really tough reasoning problems? And look, this isn't just a theory. Check out this data. On a super difficult abstract reasoning test, this new universal reasoning model, or URM, scores a whopping 53.8%. And we're not talking about a tiny improvement here. That is a huge leap over the models that came before it. So what's the secret sauce? To really get how the URM works its magic, we first have to understand that there are two totally different ways to build one of these AI models. It really comes down to a simple choice. Do you stack a bunch of layers, or do you loop over just one? Okay, think of it like this. A standard AI model is kind of like an assembly line. Every layer is a different worker that does one specific job and then just passes the product down the line. But a universal transformer, that's more like a master craftsperson who takes one thing and just works on it, refines it over and over again until it's absolutely perfect. So with a standard model, the input goes through this fixed path. It hits layer 1, then layer 2, and so on, in a straight line. The number of steps it can think is totally locked to the number of layers it has. More layers means more computing power, sure, but it's just one path, start to finish. The universal transformer, though, now that's a different beast. It's what we call recurrent. It takes the input and processes it with the same layer again and again, looping, and making its understanding better with each pass. This lets it decide how much thinking it needs to do without just getting bigger. And this right here, this looping, that's the key.
Yeah, that whole looping thing, that's everything. And what this research shows is that for really complex reasoning, being efficient is so much more important than just having raw, massive size.
And hey, don't just take my word for it. This comes straight from the paper. The secret isn't some brand new, complicated gadget. It's what they call a recurrent inductive bias. Fancy words, I know, but all it really means is that the model is just built to think iteratively, to circle back on a problem and refine its answer. And that, it turns out, is a way better method for solving these hard puzzles. And if you need proof, just look at these numbers. It's kind of wild. A universal transformer, the looping one, with only 4 times the base number of parameters, scores 40%. A standard vanilla model that's a massive 32 times bigger, it only gets 23.75%. I mean, it's not even a contest. The smaller, smarter model is just way more efficient. So, its success really boils down to 2 core ideas. First, recurrent computation. That's the power to loop and just keep chipping away at a problem. And second, strong nonlinearity. That just means the model is incredibly good at figuring out the complex, hidden rules inside these abstract puzzles. So, with this foundation, the researchers thought, okay, what if we took this already awesome universal transformer and just supercharged it? They didn't start over. They just made 2 very clever upgrades to create the URM. And these 2 upgrades are designed to do one thing: crank up what already makes the universal transformer great at reasoning. They boost its ability to spot local patterns and to focus its learning exactly where it's needed most. First up is something called Conswiglu. Yeah, I know, it's a total mouthful, but the idea behind it is actually pretty simple. It basically gives the model better local vision, helping it see how tiny pieces of a puzzle that are right next to each other are related. And you can literally see the difference it makes. On the left, you've got the standard way of doing things. Kind of blurry, right? But on the right, with this new module, wow, everything is so much more structured and focused. The model is clearly picking up on way more complex patterns, all thanks to that better local vision. The second upgrade is all about how it learns. Imagine you're studying for a huge exam. You're not going to go back and relearn basic addition, right? No, you're going to focus your energy on the hardest calculus problems at the end. Well, that's exactly what truncated backpropagation does for the AI. It tells it to concentrate its learning on those final, most difficult loops. And again, the numbers show this strategy just plain works. You see that sweet spot right in the middle? That's where the magic happens.
Performance is best when it lets the model do a couple of loops just to process the problem, and then it focuses all of its learning power on those final complex steps. It's the perfect balance.
So what happens when you put it all together? You take that super efficient looping architecture, you give it that sharp local vision, and you teach it to study smarter. Well, you get a new champion in abstract reasoning.
I mean, just look at these results. The URM isn't just edging out the competition, it is absolutely dominating across the board. Look at ARC AGI2, jumping from around 5% to 16%. That is insane. It's even a Sudoku wizard.
But if there's one number you walk away with today, it's this one, 53.8%. That's a new record. And it was set by a small model, trained from the ground up. This really proves that a smarter design can absolutely beat brute force power. And here's the kicker. The paper points out that the more you let the URM think about a problem, the bigger its lead gets. So this isn't just a fluke. It shows the model has a genuinely deeper, more robust way of reasoning about the world. So it all comes back to that first big question, doesn't it? As we chase after the next breakthrough in AI, should we just keep building bigger and bigger machines? Or should we focus on building smarter ones? This research makes a pretty powerful argument that maybe, just maybe, the clever path is the right one.